All right, so let's take a look at a few examples here on how to predict water solubility for some of these ionic compounds. So we have lead 2 nitrate, lead iodide, silver acetate, sodium phosphate, and cobalt 2 carbonate. So the first one, lead nitrate. So when you look at nitrate ion here, it's one of the large oxyanions, NO3 minus. So it says over here, ionic compounds containing nitrates will always be soluble in water. So for the first one, should be soluble. All right, and for the second one here, we have lead iodide. So an iodide is a halide, which is this one right here. It's usually soluble unless it's paired with lead or silver, and it is paired with lead, and so this is going to be insoluble. Third one here, we have silver acetate, and we have an acetate ion here, C2H3O2, which is this one right here. Any ionic compounds containing acetate ion will always be soluble in water. So this is soluble. All right. And what about sodium phosphate? So when you look at sodium phosphate, we have phosphate right here, and it says insoluble unless it's paired with the alkali metal ions. And so we have sodium here, always soluble in water. So that means that sodium phosphate is soluble in water. And the last one here, we have cobalt 2 carbonate. So we have carbonate ion right here, insoluble unless paired with alkali metal ions or ammonium. And so cobalt is not one of those exceptions and therefore insoluble in water. All right. So now we're getting into the next chapter here, which is chapter 7. Okay, so we talked about atomic mass, formula mass, and molar mass. What's the difference between uh, these types of masses? Let's take a look. So when you look at a periodic table, you'll see two numbers above and below the elemental symbol. So for example, carbon, you have 6. This tells you the atomic number, right? It tells you the number of protons and also the number of electrons. The number at the bottom is the atomic mass. And the atomic mass is the weighted average of all the isotopes of that element. When you look at this molecule right here, which is glucose, it's sugar, it has 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen in its chemical formula. And so when you add up the atomic masses of glucose, right? So you have 6 times 12.01, 12 times 1.01, 6 times 16. Again, these numbers right here are the atomic masses of the elements. And when you add them all together, you get, and so this number here, 180.16, is known as the formula mass of the compound. So glucose has a formula mass of 180.16 atomic mass unit. You also learned that formula mass is actually the same as the molar mass numerically. Okay, the only difference is the units. For formula mass, the unit is in AMU, atomic mass unit, but for molar mass, it's in grams per mole. Okay, molar mass is in grams per mole. And so that means that glucose C6H12O6 has a molar mass the same as this one right here, right? Exact same one numerically. The only difference is the units, right? So instead of AMU, the molar mass is in grams per mole. All right, the next concept here is mass percent composition. You should be able to calculate the elemental mass percent in a given chemical formula. So mass percent of an element can be calculated using this equation shown here. So all you have to do is calculate the total formula mass of the element in that chemical formula divided by the total formula mass of the compound multiplied by 100%. Here's an example. What is the percent iron in iron 3 oxide, Fe2O3? So the first thing that you want to do is to calculate the formula mass of the elements and the compound. Okay, so the formula mass of, or the atomic mass of iron is 55.85. Multiply that by 2. Do the same thing for oxygen, 3 times 16, and then add them together, and we get 159.7 AMU. Right, again, for the formula mass of the compound. The total formula mass of iron, which is what's being asked here, is 111.7 AMU, right? So that's the total formula mass of iron. So now that we have these numbers right here, all we have to do now is plug it into this equation. 111.7 AMU divided by the total formula mass, which is 159.7, multiplied by 100%, and we get 69.94% iron. All right, moving on here. Concept number 9, I believe we're halfway. Avogadro's number, right? So Avogadro's number has a symbol Na here. A being Avogadro, N for number, Na. So Avogadro's number is a huge number, right? 6.02 times 10 to the 23rd power. That's Avogadro's number. 1 mole, so we have a unit in chemistry called the mole. 1 mole is equivalent to Avogadro's number, which is 6.02 times 10 to the 23rd power. So if you have 1 mole of coins or anything, then that means you have 6.02 times 10 to the 23rd number of coins. If you have 10 moles of coins, all you have to do is multiply 10 by Avogadro's number. So 10 times 6.02 times 10 to the 23rd power, and you get a total of 6.02 times 10 to the 24th number of coins. All right, so let's go back to this right here, the atomic mass, right? The atomic mass of a carbon atom is 12.01, and the atomic mass is actually equivalent to the molar mass numerically, kind of like the formula mass. Again, the only difference between them is the units. The atomic mass uses the atomic mass unit, AMU, and molar mass uses grams per mole. Okay, so that means that carbon having an atomic mass of 12.01 AMU has a molar mass of 12.01 grams per mole. Again, the difference here is the unit here, grams per mole. So the molar mass tells you the mass of the atom or the molecule per 1 mole of the substance. Okay, so for example here, 1 mole of carbon, 1 mole of carbon would weigh 12.01 grams. Okay, so 1 mole of carbon, according to this molar mass, weighs 12.01 grams. And so that means that if you have Avogadro's number of carbon atoms, right, because 1 mole is equivalent to Avogadro's number here. So if you have this many carbon atoms, they would weigh a total of 12.01 grams. All right, the next concept here is how to convert between mass, number of moles, and number of particles. All right, so here's a diagram that can help you um, convert from grams to moles to number of atoms, molecules, or units. Units as in for ionic compounds. All right, so here you can convert from mass to number of moles going in this direction, mass to moles, by using an equation, right? So you don't have to always use dimensional analysis, but uh, if you've gotten used to using dimensional analysis, you're more than welcome to use that process. In fact, it's a lot easier to use. But if you're one of those students that can't follow dimensional analysis, you can use formulas or equations. And I provided an equation here that you can use. So in order to convert grams of whatever substance you have into moles, all you have to do is divide that mass in grams by its molar mass of the compound. All right, so that would convert it to moles. You can also go from moles to mass. So if you're given the number of moles of the substance and you want to find out the mass of the compound, all you have to do is multiply the given number of moles by its molar mass. All right. What about converting from moles to number of atoms, molecules, or units? So if you're given the number of moles and you want to convert it to the number of atoms, all you have to do is multiply the number of moles given by Avogadro's number. Okay, so let's say you're given 0.5 mole of carbon atoms, 0.5 moles of carbon, and you want to convert that to number of carbon atoms. All you have to do is multiply 0.5 by Avogadro's number. And if you were given the number of atoms instead and asking you to convert that to number of moles, you go the opposite way and you would divide it by Avogadro's number. So you divide the number of atoms by Avogadro's number and you get the number of moles. All right, so let's take a look at a few examples here. First example is asking you to convert 42.3 grams of sulfur trioxide to number of moles. Right? So according to this shortcut here or diagram, if you want to convert mass to moles, all you have to do is divide the mass in grams, which is given right here, by the molar mass of the substance. So you have to determine the molar mass of sulfur trioxide. So the molar mass of sulfur trioxide, after calculating it, is 80.06 grams per mole. So all you have to do now is divide 42.3 by 80.06, and you get 0.528 mole of sulfur trioxide. Second example here is converting 0.528 mole of sulfur trioxide to number of molecules. So now we have moles of sulfur trioxide. We're right here, and we want to convert this to number of atoms or number of molecules. Right, so we would multiply the number of moles of sulfur trioxide by Avogadro's number, and that's it. So here it is, 0.528 mole multiplied by Avogadro's number, and we get the number of molecules. In this case, 3.18 times 10 to the 23rd power. And the third example here is converting the number of molecules to number of moles of carbon. Right, so we're going from number of molecules on the right hand side to the number of moles of carbon. So all you have to do, it says, according to this, you divide the number of molecules by Avogadro's number. So 7.23 times 10 to the 21st power divided by Avogadro's number. Plug it into the calculator and you get 0.012 mole of carbon. All right, a question on the test might be converting from number of molecules all the way to mass in grams. So you would have to follow these steps here, right? From number of molecules, convert that to number of moles by simply dividing it by Avogadro's number. And from here, you multiply it by the molar mass of the compound or the substance to get the mass in grams. So for example, here, you already have the moles of the carbon. All you have to do is multiply this by the molar mass of carbon to get the mass of carbon in grams. All right. Concept number 11 here is regarding stoichiometry. So we're going to take a look at three different types of stoichiometry problem. The first one is mole to mole, second one is mole to mass or mass to mole, and the third one is mass to mass type of problem. So again, stoichiometry by definition is the quantitative relationship between the reactants and products in a chemical reaction. So let's take a look at this first type of stoichiometry problem, mole to mole. So let's say that we have this combustion reaction here of ethane gas. So when ethane reacts with oxygen gas, it produces carbon dioxide and water. So this is already balanced for you. So in this balanced chemical reaction equation, it tells you that for every 2 moles of C2H6 reacted, it will always react with 7 moles of oxygen gas. Okay, so in that ratio, 2 to 7. So the ratio is 2 to 7 between ethane and oxygen gas, or you can reverse this 7 oxygen gas to 2 C2H6. Okay, so you can turn it into fraction either way, both ways, doesn't matter. All right, this chemical reaction equation also tells you that for every 2 moles of C2H6, 4 moles of carbon dioxide will be produced. All right, assuming that all 2 moles of ethane reacts completely with oxygen gas, then you should get a maximum of 4 moles of carbon dioxide generated by this chemical reaction. And so the ratio between them in that case is 2 to 4. All right, 2 C2H6 for every 4 CO2, or you have 4 CO2 for every 2 C2H6. Here's an example. So now we're looking at mole-to-mole stoichiometry problem here. How many moles of oxygen gas is required to react to produce 20 moles of carbon dioxide? So you're given the moles of O2, I'm sorry, it's asking for the moles of O2 given the moles of CO2. So they call this mole to mole because everything is in moles. So we're going to write down what we started out with. So we have 20 moles of CO2 and it's asking moles of O2. So we're going to take a look at the mole relationship, the mole ratio between the two compounds in question. Right? So we have carbon dioxide and O2 and the ratio is 4 to 7. So here's 20 moles of carbon dioxide. And what you can do is multiply it by its mole ratio, right? And the mole ratio is 7 to 4. So you want moles of carbon dioxide at the bottom and the moles of oxygen, which is what we want, up top. Okay, so the moles of carbon dioxide here will cancel. And what's left is what we want, the number of moles of oxygen gas. So now multiply the numbers up top, 20 times 7 divided by 2, and you get 35 moles of oxygen gas. So that means that if you have 20 moles of carbon dioxide generated, that means that 35 moles of oxygen gas must have reacted completely with C2H6. And here's concept number 12. So now we're looking at mole to mass type of stoichiometry problem or mass to mole stoichiometry problem. So we're going to look at the same exact chemical reaction equation here, the combustion of ethane gas. Here's an example. How many grams of carbon dioxide gas can be generated from 20 moles of C2H6? Okay, so you're given the moles of ethane gas, C2H6, and it's asking how many grams of carbon dioxide can be generated. So again, you're going to look at the mole ratio between the two compounds here in question. We have C2H6 and carbon dioxide, so it's 2 to 4. And we're going to write down what's given here. So that this is our starting point. 20 moles of C2H6. So here's the approach. We're going to determine the moles of CO2 from the moles of C2H6 using mole ratio, the mole ratio between them. And then once we determine the moles of carbon dioxide, we can convert that to mass of carbon dioxide in grams. All right, and again, you can use this chart here, right? If you have the moles of the molecule, you can convert that to grams of molecule and vice versa. All right, so we can convert this moles of carbon dioxide to mass of carbon dioxide in grams using the molar mass of carbon dioxide. All right, so let's take a look. So um, this is our starting point, 20 moles of C2H6. We're going to multiply this by the mole ratio between C2H6 and CO2. That would be 4 to 2 here, 4 carbon dioxide, 2 C2H6. All right, ethane, moles of ethane would cancel out. And what's left is the moles of carbon dioxide. But the question here is grams of carbon dioxide. So we can convert this by multiplying this with the molar mass of CO2. So we're going to add another multiplication here, multiplier, by multiplying it by the molar mass of CO2. Again, moles of CO2 would be at the bottom, so that this would cancel with this moles. And what's left is the mass in grams of CO2. All right, plug this into the calculator. 20 times 4 times 44.01 divided by 2, and we get 1,760 grams of carbon dioxide generated from 20 moles of C2H6, or ethane gas. All right, and concept number 13 here is now probably the most dreaded type of stoichiometry problem. It's mass-to-mass stoichiometry. So you're going to be given the mass of a compound, which is going to be your starting point, and you're going to convert that mass of the compound given to moles of the compound. Again, of course, using the molar mass of the compound. And then from there, you're going to be asked to determine the mass of, let's say, a product that's generated. So you would have to convert this moles of compound to the moles of the compound in question, okay, using the mole ratio. And then from there, once you've determined the moles of the compound in question, you can convert that to mass of that same compound using the molar mass of the compound. All right, so let's take a look at an example here. Again, we're using the same exact chemical reaction equation. It says if 10 grams of ethane was reacted completely, how many grams of CO2 would be generated? So it's a mass-mass stoichiometry problem because you're given the mass of a compound, and then you have to determine the mass of another compound in that chemical reaction. So the first thing we want to do is convert the mass of the compound given to the moles of that compound. So here it is. We have 10 grams. We're going to convert this to mass. We're going to convert this to moles of ethane using the molar mass of ethane, C2H6. So here it is, grams of C2H6 would be at the bottom, so that it'll cancel with this grams of C2H6. And then convert moles of C2H6 to moles of the compound in question, which is carbon dioxide, using the mole ratio. So the mole ratio here is 4:2. So we want 2 moles of C2H6 at the bottom and the 4 moles of CO2 up top. So you can see moles of C2H6 will cancel, and now we have the moles of CO2. But the question here is, what is the mass of CO2? So we have to convert this number of moles into grams using the molar mass of carbon dioxide, which would be 44.01 grams of CO2. So now you can see how the moles are canceling out, and you're left with the unit that we want, which is the mass in grams. So we're going to multiply all the numbers up top divided by all the numbers at the bottom. So that's 10 times 4 times 44.01 divided by 30.08 divided by 2. And we get 29.3 grams of carbon dioxide. So this is guaranteed will be seen on the test. So you will encounter a question similar to this on the test. All right, and the last concept that we covered in chapter 7 is regarding percent yield. All right, and this is simple, just like any other percent concept. Percent yield is calculated by dividing the actual yield by the theoretical yield multiplied by 100%. The actual yield is the actual amount that you've generated in a chemical reaction, and the theoretical yield is the calculated amount that you can potentially get in a chemical reaction equation, in a chemical reaction. So here's an example. Again, we're using the same chemical reaction here. The combustion of ethane, C2H6, produced 500 grams of water. If the theoretical yield is 575 grams, calculate the percent yield. All right, so again, when ethane was burnt, it produced 500 grams of water. According to a calculation, which is the theoretical yield here, you're supposed to get a total of 575 grams. But because not all reactions go into completion, meaning 100%, the actual yield is always lower, it's always less than the theoretical yield. And so we can get the percent yield here by dividing 500 grams by 575 grams. So plug these numbers into this equation here. 500 divided by 575 multiplied by 100%, and we get 87% yield.